Welcome back to Office Hours with Dr. Clark. So, we are going to be continuing our discussion about quantum theory, quantum mechanics. That's real high level quantum mechanics, though. I tell students if you want to go deeper in quantum mechanics, you take some higher chemistry like physical chemistry, for example. Right? So today we're going to be looking at quantum numbers. Quantum numbers. So there are four quantum numbers. There's n, which is the principal. There is L. There is m sub L and m sub S. So those are our quantum numbers that you will see in, a lot of gen chem classes. So my principal, talks about the energy or size of orbital. L is the shape. M sub L gives me the spatial orientation. And so that's just maybe the electron spin. Yep. So we're gonna really be focusing on these three. And so this is more something that you will just be given. It's gonna be plus a half. Now n, values for n is 1, 2, 3. So these are whole integers starting at 1. L starts at 0 and then goes all the way to n minus 1, whole integers. M sub L are the whole integer values from negative L to positive L. And then M sub S, like I said earlier, electron spin plus a half minus a half. Okay. So how do we break these down? Because this is going to lay the foundation for electronic configuration, orbital notation. So say my n is equal to 1. My L is going to be 0. Because there's no, so 1 minus 1 is 0. Right? My m sub L is also going to be 0. Because there's no negative 0, positive 0. Right? So n equals 1 is pretty straightforward. And when an L of 0 is an s orbital, what about n equals 2? My L values will be 0 and 1. Because remember, L only goes as far as n minus 1. So for each of these L values, we need a separate m sub L value, right? So m sub L for L of 0, my m sub L is 0. For L of 1, it's minus 1, 0, and positive 1. So we have three m sub L values. So when L is 1, that's called a p orbital. So you could think of these orbitals to think of an to think of a building. You think of your atom as a building. And then the floors in the building are your ends. So you have the first floor, second floor, third floor. And then think of the rooms as your L's. And then within those rooms, if you have like say cubicles, for example, my office is a room that has several other smaller offices. So you think of your M-sub as smaller cubicles within in a room, different partitions. And then we can put electrons, which are people like me, in these partitions. So you can represent the orbitals as boxes. So here is my three orbitals designated -1, 0, 1. So don't think of these as like out numbers that you need to do anything with mathematically. These are just labels, -1, 0. And then think of this zero or this zero here, which is an S orbital as this one box, one space. Let's look at n equals 3. My L is 0, 1, and 2. So now I have three L's. I have three rooms. Within each of these rooms, my M sub L is going to have one S orbital, one space for my S orbital is only going to be one box. Now, for my P orbitals, I'm going to have my -1, 0, and 1 again, my three boxes. When I see a 2, that's a D. My D, we have -2, -1, 0, 1, and 2. So I have 5 boxes to my D orbitals. So my D only starts at n equals 3. My P starts at n equals 2, and at n equals 1, there's only an S. So you're starting to think now about how atoms can arrange themselves. Okay, so you think of 5 cubicles in the room, in the D room. Now, if we have n equals 4, so this is, if you think of the atom, think of your nucleus. Here's my n equals 1, 2, 3. So the bigger the n number, the further away you are from the nucleus. And these n numbers are defined by energy. So the electrons that occupy these have a specific energy associated with them. And so n equals 4, my L is, what do you think L should be? Number goes as far as n minus 1. Right, so 0, 1, 2, 3. Right, so each of these L's, so the 0, 1, and 2 are already there. So it's going to be the same as we saw for the L equals 2 here, L equals 1 here, L equals 0. For the 3 now, that's the new one. 3 minus 2 minus 1, 0, 1, 2, 3. So I have 7 boxes, and this is an F orbital. Two, three, four, 6. I have 9 boxes here. Get rid of boxes. 2, 3, 4, 6, 7. Okay. And remember, this is 0. This is, so for every L, you have to give your M sub L. You have to have an M sub L for every single L. So every energy level, some of them you're going to have the same S and P's and D's, but you have to break each down individually for every level. You can't say, okay, well, it's going to be the same as the last level. You have to break them out individually. So remember, so let's kind of summarize here. If L, so here's my L value, this is really important when we start making the electronic configuration. 0 is S, 1 P, 2 D, and 3 F's. So we can think of electrons. So there's every box can hold two electrons, right? So there's some tricks. If we know that the max number of electrons in n is equal to 2n squared. So what I'm saying is my n is equal to 2. The total number of electrons that could fit on that level, right? We call it energy level or shell, is 2 times 2 squared. So that's 8. Right? So let's look at it to see if that makes sense. N equals 2. Let's go back to our n equals 2 up here. N equals 2, I have L of 0 and L of 1. So I could throw 2 electrons in here, 2 in here, 2 in here, 2 in here. That's total of 8. Right? So we can tell how many electrons max. Doesn't mean that the energy level is going to be completely filled. It just means that if it's filled up, it can only hold 8. Now we can figure out number of orbitals that a certain n level will have by n squared. So again, if n is 2, so if n is equal, let's say n is 3, that's for argument's sake, number of orbitals is going to be 9. So let's look at our n equals 3. And it's not, let's look at the math. N equals 3, so we have 0, 1, and 2. Those are our 3 L's. So that's 1 orbital. That's 1, 2, 3. So 4 orbitals. And then we have 5 here. That makes 9 orbitals. So these are some quick ways if you need to figure out how many orbitals, and you kind of check yourself. So when you're breaking them down for M, the M sub L, see if you have the right. Yep. So there's a rule, Pauli's exclusion principle states that no two electrons can have all four of the same quantum numbers. So really, this typically works out when we talk about electron spin. So let's take electron n equals 1, right? Let's say 2 electrons. So then we have L is equal to 0, and so the equal to 0. So you have your box. So if I have 2 electrons that occupy this level, they can have the same n, l, and n sub l, but they must have opposite spins. Right? So opposite spins. That's how we see an application of Pauli's exclusion principles. The spins must be opposite. Also, Hund's rule electrons occupy orbitals singly with parallel spins. So meaning, if I have, say this is a p orbital, L equals 1, p orbital, and I have 3 electrons, they're going to occupy with parallel spins. Also, with Hund's rule, each orbital must have at least electron Fill all orbitals are filled. So what I'm saying here is you'll never see something like this where you have N, A, and B doubly occupied. So what we're saying here is you'll never see something like this. I double up here, but I have an empty orbital. So that's a no. So instead, you will see this. And if I have an additional electron, then I can double up. So I'll make sure all filled. And if I have extra, then I double. Okay. And then I'll fill in principal. Fill lowest energy levels first. So we start with n equals 1, n equals 2, and so on and so forth. We don't start filling 3 upwards and neglecting 1 and 2. And then generally, we start at S and P, etc. Now, there's some exceptions if we're going to see, uh, for example, when you get to D, because sometimes there's some S's that get filled before D, but we'll talk about that in another video. All right, so just wanted to talk about some quantum numbers and how we um, look at those. So remember, um, what tends to mess students up, like for example, if I say, okay, so how many orbitals, hmm. So it's either 5, and we're like, oh, it's 5. No, that's the end value. That's the energy level. So we're on the 5th floor, if you will. What we're trying to see is how many rooms there are on the 5th floor. So since it's P, L is equal to 1, so therefore my M sub L is minus 1, 0, and 1. So I have 3 orbitals. So your P, something I didn't mention earlier, your P, these 3 orbitals, we call them P, X, P, Y, P, Z. Not necessarily linking any specific number to any of these. We're just saying that there's 3. So there's 3 different orientation of the P. So you have they look like lobes in the Y direction, and then Z is in the Z direction. Right? Um, your S, let's say this is one S, it's going to be spherical. Your D's and F's have more complicated shapes. Right? And, and generally, most, in general chemistry, most teachers might not ask you to draw all 5D orbitals or any at all. Typically, we expect you to know the shape of the S and the P's because those are fairly simple. The D's and F's, they have more complicated shapes. Like, for example, the D's looks like this. It has a lobe, and like a little circle around it. It's a D orbital example. And some other, really cool shapes. Okay, yeah, so let's keep in mind that the P here tells you that's your L value, and it's going to be specific. If you see a P, you see an S, your D is going to be a very specific L value. And this number here is your N. Right? And then to figure out how many orbitals you have, once you know your P, you can figure out your M sub. Okay, so that's all for now. Until next time, all the stars with Dr. Clark.